you very much. I can always speak up if necessary. Thank you. In person is always better than virtual. Sorry for the technical glitch. I'm Bhuvanesh Sundar from Rigetti, and today I'm going to talk about qubit-efficient quantum optimization. There's a pointer. I'm going to talk about quantum optimization because optimization problems are ubiquitous. Right from the moment I step out of the house and turn on Google Maps, or I go to a restaurant and order from a menu. When they get large, the problems are exponentially hard to solve to find the exact solution. But there are heuristic algorithms which provide candidate solutions in polynomial time. And we are interested in whether quantum heuristic algorithms can compete with or even outperform classical solvers, and at what scale. There are several quantum algorithms for solving optimization problems. You've heard a few of them in this conference. You heard about one in the previous talk, the QA, which is the quantum approximate optimization algorithm. So here, the optimization problem is expressed as a cost function, which is the expectation value of a Hamiltonian. So the quantum algorithm is minimizing the Hamiltonian. In the QA way, one executes a quantum ansatz, and it's a physically motivated ansatz motivated by tortoise adiabatic evolution. The quantum computer executes the ansatz and measures the cost, and the classical computer finds the parameters in the ansatz such that the cost is minimized. And this algorithm, or variants of it, have been successfully used to solve optimal problems at modest sizes with order 100 variables because of about 100 qubits today. But as you heard in the previous talk, 100 variables is pretty small. Classical solvers can solve much larger problems in a reasonable amount of time with 1,000 or even 10,000 variables. So how can we solve larger problems with current quantum hardware? Again, you just heard one technique to do that for large and shallow circuits. In this talk, I'm going to describe a much more general way, a fundamentally new, efficient way to store classical information in qubits. The idea in a nutshell is to use the exponential large Hilbert space qubits to store a lot of information. First, I'll explain this efficient encoding of classical information, and then I'll explain a quantum algorithm which uses this encoding to solve optimization problems. In practice, what we do is our problem has n variables. We break up those n variables into groups, into smaller groups, and we store each group of variables in a set of qubits called data qubits. Now, which group of variables is stored in data qubits is dictated by a second set of qubits, which we call the label qubits. Let me illustrate this with a concrete example. Suppose I wanted to store these 12 bits. I can, for example, break up these 12 bits into 4 groups of 3. Then I'll store the first 3 bits in the 3 data qubits if the label qubits have the value 0, 0. I'll store the next 3 bits in the 3 data qubits if the label qubits have the value 0, 1, and so on and so on. In this way, I can store all the 12 bits in these 5 qubits. Notice that this bit string is encoded in an entangled wave function of these 5 qubits, and this is a general theme of this qubit-efficient encoding. Now, there's a free parameter here, which is the grouping size, the size of the groups, or in other words, the number of qubits needed to encode these 12 bits. And I can choose different encodings, different numbers of qubits to store the same bit string. Now, this is how you store the variables in the qubits. Once you store them, how do you retrieve the variables from the quantum wave function? Well, you retrieve the wave function by retrieve the variables by projectively measuring the wave function. When you projectively measure the wave function many times, then you get a distribution of bit strings. Each subset of bit strings corresponds to one group of variables. For example, if I wanted the average value of the z variable zi, then I would just calculate the average value of the poly z on that data qubit from that subset of bit strings. If I wanted the average correlation zi, zj between 2 variables in a group, then I would just calculate the average value of the poly zi operator multiplied with the poly zj operator on those data qubits from that subset of bit strings. There's one exception to this. If I want the correlation zi, zj between 2 variables in 2 different groups, then they are never measured together. In that case, we define the average value of zi, zj as the product of the average zi and the average zj. These are expressed formally in terms of expectation values here. This construction can be extended to estimate any polynomial in the z variables, and that's useful because cost functions for optimization problems are typically polynomials in the z variables. So we can express any cost function in terms of this qubit-efficient wave function. Now, these are the ingredients from a quantum algorithm. The quantum algorithm is a variational algorithm where we execute a quantum ansatz and measure the cost function using the procedure I described in the previous slide. In the ansatz, we implement the problem Hamiltonian and 1 qubit. And the problem Hamiltonian here is such that the cost is the expectation value of the problem Hamiltonian. Now, a key difference here is that because of the qubit efficient encoding, the problem Hamiltonian depends on the state, depends on the wave function xi. In practice, what this means for the ansatz is that in any given layer, the problem Hamiltonian in that layer has to be estimated by projectively measuring the wave function in the previous layer. So this completes our algorithm. So we implement this quantum ansatz, measure the cost, and the classical computer finds the parameters in the ansatz such that the cost is minimized. We implemented this algorithm first for an ensemble of spin glass problems, Sherrington-Kirkpatrick problems, which are quadratic cost functions where the spins interact randomly. We plot here the average approximation ratio for an ensemble of problems versus the QAOA depth. The approximation ratio is just the ratio between the cost produced by the quantum ansatz and the actual ground state cost. So if the approximation ratio is 1, then we found the exact solution. These different curves with different colors correspond to different numbers of qubits for the same problem, different qubit efficient encoding for the same problem. And the curve in black is the traditional QAOA, which uses 64 qubits for 64 spins. Well, first we find that the approximation ratio increases. It increases towards 1 as the QAOA depth increases, and that's great. We also find that the approximation ratio for the qubit efficient encodings is smaller than the approximation ratio in the QAOA. Nevertheless, they are still competitive. The approximation ratio at depth 3 and 4, for example, is competitive, is comparable with the QAOA's performance at depth 1 and 2, despite requiring much more qubits. We find similar trends for larger problems with 128 spins. Now, this is a toy problem that is paradigmatic in statistical mechanics, optimization, and computer science. Next, we consider a slightly more relevant problem that's closer to real-world problems, which is a traveling salesman problem. And the goal here is to find the shortest possible route on a map that traverses all the points, all the cities on a map, such that each city is visited exactly once, and we return to the starting point. This problem is expressed as a cost function, and the cost is nothing but the length of the route, the distance of the route, plus the two constraints that are listed here. Mathematically, these are the terms that are in the cost function. I'll just note that the constraints here are implemented as penalty terms in the bit string. So if a bit string violates a constraint, then it incurs a large penalty. We implemented qubit efficient ansatz for the traveling salesman problem. And here's what we found for synthetic traveling salesman problems with 10 and 20 cities each, where we randomly pick the distance between two cities as an integer between 1 and 10. We plot the approximation ratio versus the QAOA depth for different qubit efficient encodings. Each color corresponds to a different number of qubits for the same problem. And we find the approximation ratios approach 1 as the depth increases. And if you find an approximation ratio 1, that means we have exactly solved the problem. I should note that it's not just the quantum ansatz here. I'm also doing some classical post-processing after this to enforce the constraints. So this is great. This again tells us that the qubit efficient ansatz can work for different kinds of optimization problems and produces promising results. At the beginning of my talk, I told you optimization is ubiquitous. We see it everywhere around us. So it'll be useful to see it applied to an actual real problem. So here's one example from the traveling salesman literature, traveling around the US. Suppose one wants to visit all the 48 states in mainland US, except Hawaii, and one wants to visit all the capitals. Someone has solved this problem exactly, and the optimal solution has a route whose length is 10,600 miles. In Berkeley, for example, you can start at Sacramento and go up to Portland and Seattle, come down to Boise, and so on. The qubit efficient ansatz at just one layer, p equals 1 QAOA, produces a solution which looks like this. Its length is 11,200 miles. It is not the optimal solution, but it's close, and you can just tell by looking at it that it looks reasonable. This is in comparison to two other classical algorithms. One is a greedy algorithm where one just goes from one city to whatever is closest to it. And it produces a solution whose length is 12,800 miles. So it just looks wrong. You can tell by looking that there are clearly mistakes in the northeast, in the middle, and so on. And then one other algorithm, which is more sophisticated, it's an approximation algorithm which guarantees that it will never find a solution that is worse than 50% from the optimal solution. But it just looks horribly wrong. You can looking that this road is weird. And the actual length of the road is 14,500 miles. So our quantum ansatz perform better than to simple classical algorithms. I want to finish Qubit-efficient encoding for solving large problems, quantum computers. Is that classical variables encoded in functions with fewer qubits. We believe it would be useful for NISQ computers as well as fault-tolerant computers because fault-tolerant computers in the near future are expected to be small with few qubits. And so techniques like this could be useful for solving larger optimization problems using few fault-tolerant qubits. That's it. Thank you for your attention.
Thank you again.